Okay, so what I'd like to do is talk a little bit about some new material now of moving on to section 4.3, which is on composition and inverse functions. So just to give a little bit of a definition of what we're looking at here. So we're going to have a function f. It's going to be mapping a to b, and g is going to be a second function that's going to map b over to c. So the composition of functions, hopefully you've all seen this at some point in your careers. What the composition is defined as is it's going to be this function g of f. So we have this little composition circle that's going to say a maps to c is this new function defined by saying the composition of g with f is just g of f of x. Okay, so hopefully, when I say composition of functions, as I said, that this does ring a bell with things in the past. Now, it's going to look obviously a little bit different in this class. So to visualize thinking about the domains and codomains, what's happening is we're saying that f is going to take things with a domain of A into the codomain of B. For us to have a well-defined composition, that we now need to be able to take all of this from B and be able to map it into C. So when we look at these two functions, notice that the codomain of f is b and the domain of g is b. So we have to have the same codomain of the first function as the domain of the second function. If we didn't, well, then we might have issues of having every element in the domain of G be mapped to elements, or be able to have something that gets mapped to something in C. So we have this regular idea of these two functions, but the composition basically is going to take these elements in A and just pop them right out into C. So we essentially somewhat skip this as long as everything is okay with having the domain and the codomain of these two being the same. So when we now want to look at some questions about composition of functions, one of the first questions that we have to ask ourselves is, does the composition of f with g, is this commutative? So is f composed with g the same as g composed with f? Now, remember, this one, the one on the right is always the one that's happening first. So we're saying that we're going to plug things into G does something, and then F is going to do something here. As opposed to this one, we're letting F do something first, and then G is going to be doing something else. Are these commutative? Good job, exactly. So no, a big resounding no I heard through the screen. Good job, everyone. So what we should be thinking are some examples that show this. So if we have this be equal to x squared, let's say f is going to be equal to x squared, where f is going to map the reals into the reals, and then g of x, let's say this would be something like x plus 1, and g is going to map the reals into the reals. So this is a function. As a piece of advice, usually with these, if I can do reals to reals, I'll do reals to reals. It just makes it a lot easier. Then I don't have to worry about these matching up. So when we look at the composition of g composed with f of x, well, we said over here that we defined that as g of f of x. So this was g of f of x. So this is going to be g of x squared, and this is going to be x squared plus 1. But if we do it in the other order, we now have f of g of x. And so this is going to be f of x plus 1, and this becomes x plus 1 quantity squared, which is x squared plus 2x plus 1. And so we see that indeed this x squared plus 1 is not the same thing as x squared plus 2x plus 1. So obviously functions, the composition of functions is not commutative. Now, hopefully you've seen examples like this in the past. It's fine if you haven't. But moving forward, we'd like to now delve into a new area on inverses and how does this, the idea that the composition of functions is not commutative, how does that affect inverse functions?